Today I'll speak about automating innovation and discovery with machine learning. So this is the story of my PhD so far at the Hebrew University with Daphna Shachaf. So how many of you know this one from Matt Might? Okay, so that's good. Don't spoil it for the rest of us. So imagine a circle that contains all of human knowledge. And by the time you go to elementary school, you learn this much. By the time you finish high school, you learn some more. Then in your bachelor's degree, you gain a specialization. And in your master's degree, you deepen the specialization. And then you read research papers. Then you read and you read, and you get to the boundary of humanity's knowledge. Then you start focusing, and you focus for a few years. You push at that boundary, until finally one day that boundary gives way and this dent you create is called a PhD. And that's me, hopefully, celebrating it. Now, getting a PhD is great, but we have a couple of problems. First, as humanity's knowledge keeps growing and growing, it's getting exceedingly hard for any one individual to reach that boundary. And second, a lot of important inventions across history involved connecting the dots between fields and not only reaching the boundary of one. So take, for example, the ancient Greeks. More than 2,000 years ago, they studied the properties of sound waves by analogy to water waves. And there's lots of different examples. You can take the Wright brothers who innovated in flight by taking ideas from bicycles. More recently, NASA was inspired by origami to design parts of their spacecraft. And the problem here is that in order to connect the dots between two different fields, you first have to know that they exist in the first place, right? And then you have to have quite deep understanding in each of them in order to do and make a proper connection. And this, of course, is not feasible to do at scale across many fields and many ideas for any given person. On the other hand, it's never been actually easier for us to get our hands on ideas. We have millions of patents, scientific publications, crowdsourced innovation sites, many more sources, all of which present us with an opportunity to accelerate problem solving, to boost innovation and discovery by finding inspirations and connecting the dots and identifying promising new directions. But there's also a big challenge. These large, messy data sets are hard for us to work with. And the question is, how can we help automate this process of discovery and innovation? So in this talk, I'll discuss two things. First, boosting creativity with analogies, and then identifying novel directions with a weak supervision framework we developed. So let's start with analogies. A lot of important inventions across history involved analogies. We saw a few examples. Let's see a few more. Thomas Edison, the famous inventor, actually said that an important quality of an inventor is a logical mind that sees analogies. And he used analogies all throughout his own innovation process. We have an analogy from slot machines to bacteria mutation that later won a Nobel Prize. Closer to our own field, we have, for example, genetic algorithms and simulated annealing, all kinds of optimization approaches inspired by nature. And there's many, many more examples. Now, a different kind of example, a recent example, is of a car mechanic who saw an invention enabling to extract babies stuck inside a birth canal. And the World Health Organization actually recently said that this is one of the most important inventions in this area in many, many years. Now, the cool thing for us about this invention that it actually comes from a random party trick the car mechanic found on YouTube, showing how to extract a cork stuck inside a wine bottle. And by analogy to this cork extraction mechanism, he came up with a completely new idea. So we'd like to take this kind of process of innovation by analogy to automatically discover these analogies in large data sets and help boost innovation by using them. Now, the problem with automation is that analogies are hard for machines. NLP and information retrieval methods, as I'm sure we all know, excel at surface similarity when we have similar source and target domains. So for example, you could take this scraper that scrapes ice off your car, and then you could have burnt oil stuck onto a kitchen pan. And in both domains, we see this kind of abstract relation of material stuck onto some surface, and we'd like to remove it, but described in completely different distributions of language. Now, what was done in the early days of the field called computational analogy is creating manually curated databases with this kind of crazy predicate logic kind of structure. So here, for example, you can see what this kind of structure may look like for that cork extraction device that we saw before. And as we can immediately see, it's not feasible. It simply would not scale. It could take a huge amount of hours to extract for real products. Now, we do want to try and work with the data we have. So we go to a site called Quirky, which is a crowdsourced innovation site, and we collect crowdsourced product ideas coming from many different categories, which is a good thing because we want to learn analogies across domains. And these are written by ordinary people in the kind of messy variant of natural language. You can see one example here. By the way, can you see? Am I blocking your view there? Okay, good. And our first kind of attempt is let's try some supervised learning. So we collect some labeled data. We build a search interface on top of Quirky, and allowing workers to find us examples of analogies. So for example, we give them a seed product, and then we have them search for examples of analogies. And when they find one, they give us a match. This way, we collect our positive examples. We also collect negative examples, the implicit negatives as a standard information retrieval. Top results a user viewed but did not select as a match. And we also collect the query. Now, in our first work, we learned a similarity metric reflecting analogy. I won't go into too many details about this one, but we trained a CNN-based network with the contrastive loss, and we incorporated in the user query as a kind of anchor because that is what the user uses input to find analogies. And we help the model in this way focus on the non-surface features. Now, the good thing about this model was that in terms of accuracy, we were able to beat all kinds of standard retrieval baselines, and the query indeed helped us further improve our results. But the bad news was that labels were costly, noisy, and slow to obtain. It's a hard task for humans. People tend to be much better at finding surface matches, like phones and different kinds of phones. This is well studied in cognitive psychology. And because it's a hard, yeah, sure.
Can you send me through what exactly was the task? I mean, you were given a problem and you were looking for a solution from a different domain?
So in our case, we were given pairs of products and we want to identify whether they are analogies or not with respect to the labels we collected from the crowd, which are noisy and tend to focus on surface matches. Exactly. Yeah, exactly. In addition, another kind of variant of the task is search. So we also collect the query, and then we can help guide the model at test time when the user is searching for new ideas by anchoring via the query to focus on less surface features. But because it's indeed a noisy annotation process and slow, we didn't have much data. And the model, this is important, was left blind to the kind of rich structures that go into analogy. And it's really not realistic to expect our model to learn this from raw text with that kind of data. So in our second work, we're going for a more structural representation. And our goal here is to find a structure that's expressive enough for analogy mining, but also simple enough to be learned. So somewhere in between that raw text and that kind of crazy elaborate structure that we saw before. So we focused on the purposes and mechanisms of ideas. And these are rooted in cognitive psychology that tells us that analogies are deeply related to these concepts. And in terms of purpose, we can simply think about, well, what does a product do? So we have this scraper here, and it removes ice from your car. And its mechanism, how it works, is with a brush, a blade, and a grip. Now let's assume for a moment we have these representations. We can do some core tasks. For example, finding two products that share purposes but have very different mechanisms. Or we can do what's known as repurposing, finding two products that share mechanisms but have very different purposes. For example, that cork extraction device used for a completely different purpose of easing childbirth. So our goal in this work is going to be to learn vector representations, capturing the purposes and mechanisms of inventions, and then using them to find analogies and boosting creativity. Okay, so we first collect some data again. We go to Mechanical Turk, and we collect annotations corresponding to purposes and mechanisms of texts. Now in this work, we want to learn a soft vector representation corresponding to the overall aggregate notion of the purpose and mechanism of an idea. So what we do is simply this. We aggregate across our K workers. We learn purpose and mechanism TF-IDF weights over our corpus with respect to each one of these aspects. Then we compute a weighted average of our Glove pre-trained vectors for the purpose and mechanism parts of the text across workers. And then we get these two target vectors. One is a target purpose vector, and the other is a target mechanism vector. And our goal now is to learn to extract these vectors for new products. Now, just one quick note here, because we also have somewhere in there a normalization layer, normalizing the activations of the purposes and mechanisms. So actually by minimizing the MSE, we in fact minimize the cosine distance. So we're finding vectors that are in the same kind of direction of the purpose and mechanism target vectors, hopefully allowing us to capture a bit more abstraction. Now we evaluate this on that test set we curated with that search engine we showed before. And we see that we're able to beat all kinds of retrieval approaches and text representations, sometimes by a large margin. And this is despite two things. First, having noisy purpose and mechanism annotations. We're doing this at a scalable approach, collecting noisy annotations and seeing if they are useful enough for us. And secondly, an important point is, as we said, people tend to focus on the surface analogies. So phones and different kinds of phones, as we said. And these surface analogies, we have quite a high proportion of them in our test set. And these obviously favor the surface-based approaches, as in standard NLP. And we're able to retrieve those surface matches in addition to the more distant ones with our approach. Okay, so quick reality check. As a side note, we also took our output predicted vectors on the test set. We wanted to see if we can interpret them. Of course, there are various ways to do this. We simply model them with kind of a sparse coding approach that's sometimes used to analyze word vectors. And we took a sparse linear combination of words in our vocabulary. And we indeed see that for lots of products, we have some more examples in our paper, the mechanism words of a more mechanical nature and the purpose words of a more kind of purpose-oriented nature. So that was evaluation in terms of accuracy, but our main evaluation goes back to our motivation of boosting creativity. And we do this in an ideation setting, which is a common creative task. You often see it in psychology and in design firms, asking people to redesign an existing product. And we want to find new ways to solve the same problem. So in this case, we give people a cell phone charger case, for example, and we ask them to find new ways to charge your phone. And we give them random inspirations. We also give surface inspirations, what you'd get from standard search, for example. And with our approach, we aim to find a near-purpose, far-mechanism set of analogies because we're looking to find new ways to solve the same problem. And our assumption or hope is that this approach will help explore the design space in a more diverse way. So sharing this diversity of the random approach, but also the relevance of the standard search surface-based approach. So what kind of inspirations do we get? Well, random, of course, is all over the place. So for example, we have this dog meetup app, which I'm sure you all have installed on your phones right now. In surface standard search, we have very relevant things like more cases and batteries, but not very diverse, not very inspiring. And in our approach, first we see that we were able to retrieve two things related to charging, not necessarily at all for phones. And secondly, one of our top retrieved results is a human pulley-powered generator suit. It's kind of a silly invention. It generates power using your movement. But in an abstract way, it's related to the purpose of generating power, but with a mechanism that completely doesn't mention phones. Phones are not even remotely mentioned in this product. So people, when they viewed this inspiration, actually came up, quite a lot of them, well, you can probably guess with what, with generating power for your phone by kinetic energy during walking. And to make this more quantitative, we gave these hundreds of ideas to a panel of external judges, and we had them rate according to standard ideation protocol. Novelty, quality, and feasibility, which basically means don't defy the laws of nature. So you could come up with a great time travel machine, could be great and very novel and high quality, but feasibility not so much. And we first observed substantial judge agreement between the judges with respect to these ideation criteria. And when we look at our results, we see that both in terms of relative and absolute numbers, our approach generates a considerable large positive effect. So the bottom line here, the takeaway, is that our approach yields a substantial increase in people's creative ability by using inspirations inspired by analogies. One quick note about a further application, downstream application. We took this another step forward in boosting science. So now we want to find analogies between scientific papers. So we first slightly extend our annotation scheme to include background and findings annotations to better separate the purposes and mechanisms. And we worked with a biomechanical engineering research group that wanted to find inspirations and novel applications. And this group had quite bad experience with standard academic search. I'm sure that not with Semantic Scholar, of course, but with the other competitors. And they had like near direct replication of the lab's work. While with our analogy-based approach, they were able to find results that were judged as both relevant and new. These out-of-domain alternative approaches that were never actually seen by the lab and judged as useful in user studies. Okay, so we saw models that take in the raw text, and then we moved to have more structure with those soft aggregate purpose and mechanism vectors. We slightly added some more structure and refined it for science, and now we're taking another step. We want to move from soft vectors to fine-grained functional models. So we're still collecting annotations of the text with respect to purpose and mechanism, but we update our annotation scheme and approach in all kinds of ways, and this is discussed in our recent paper, which is under review, and as by the way, it's joint work with Ronen Tamari, who's sitting here. And our objective now, though, is to learn to extract spans of the text corresponding to purposes and mechanisms. And this is important for us because it enables new applications, downstream applications, which we'll discuss in the next slides. Now, another step we want to take in this work is to move to patent data. Now, this is a really important large-scale source of engineering innovation. It's kind of an index of technology. It's much larger than Quirky. So Quirky is a challenging data set in terms of noise and language, but it's much smaller. And patents can importantly enable us potentially to discover many more purposes, many more mechanisms and analogies with direct implications for engineering. Patents also, unfortunately, are kind of a messy creature. So you can take a look at this common guideline for patent examiners and writers. It appears in all their textbooks. So the subject matter of the invention should be described in one or more clear, concise sentences or paragraphs. Oh, well, not really the case. Here's one patent sentence. Forget about being concise. And about clarity, patents often use this kind of obfuscated language. Take a look at this patent, for example, dating back to 2001. It speaks about a circular transportation facilitation device. And it goes on and on about it until you reach the patent figures. And then you find out it's actually reinventing the wheel. This is a true patent, true story, was accepted. It later won the Ig Nobel Prize, and then, only then, it was silently removed by the patent office. So this goes to show you a lot about patents. Now, Annotating purposes and mechanisms, it was hard enough in quirky. In patterns, it's going to be harder. We have these long obfuscated sentences and all those characteristics I mentioned. In addition, patents, they're written by lawyers, and they often kind of skirt around the purposes, not really telling you what it is actually about, all kinds of technicalities. So we try to ease this by sampling from domains that are easier for crowds to understand. There's some of them. But we still get noisy annotations. With partial tagging, workers in addition also skip a lot of sentences, presumably because they are so hard to read. So we're working here in a low resource, noisy annotation setting with noisy texts and annotated by complete non-experts. This is kind of very far from what you often see in NLP benchmarks. So looking at our characteristics both in quirky and in patterns combined, we realized that a graph representation can help us. And this graph will capture both syntactic relations, well known to exist for purposes and mechanisms. And for this, we'll use the dependency parse tree to capture these more local syntactic structures. But we also want semantic relations to propagate information across long spans of the text. And this, we assume, will be particularly useful for patents. And we do this with an embedding-based similarity across different parts of the text. And to make this more concrete, our model is a contextualized graph convolutional net. We have multi-channel input embeddings, which include the pre-trained glow vectors, but also other rich pre-trained information like part-of-speech tags, named entity recognition, dependency parse information. We feed that into a BILSTM to capture our sequential context. And then the outputs emitted by the BILSTM are fed into a relational graph convolutional network. And the nodes in this graph correspond to our tokens, right? And then we run multiple layers of this convolution, finally outputting the node representations into a CRF layer to capture tag dependencies. Now, as baselines, we first took a BILSTM CRF. We enriched it with the same multi-channel input embeddings that we see before to capture syntactic and semantic information in our data scarce setting. And then we also, in an ablation study, studied the different properties of our edges and what contributes more. And I'll give you the bottom line. First, our graph model significantly improves results. And interestingly for us, the longer range semantic edges indeed help, especially for patents, which is what we hope for. The overall accuracy is low in relative terms. It's a noisy task, noisy training annotations, noisy language, pretty challenging. And we actually see that our model's predictions are often better than what you get from the workers as so-called ground truth. So here are two annotations for the same product, and let's zoom in to see what's happening. So the crowd, for example, gives us a mechanism annotation for a travel mug. And our model extends that mechanism annotation to a dual heated travel mug. And in addition, also adds a purpose, you keeping your coffee warm as you go. So because these annotations are not super reliable on the test set, we focus on a gold standard test set that we curate, which is much more reliable. And we also add some self-training and semi-supervised approach to propagate our labeled information to all those many sentences that were left unannotated by the crowd so that we can still use them. And we see that this indeed significantly boosts results, especially for patents where it really increased recall as you would expect. So that was an evaluation in terms of accuracy. We now want to focus again on what truly interests us, which is how useful are these models? And can we use them for our applications? And unlike our soft aggregate vectors, we now have finer granularity and interpretability, which will support the applications that we'll go into now. So the first application, is building a Commonsense functional ontology. And we want to map the landscape of ideas with a purpose mechanism hierarchy coming from real-world product texts. This has important implications for engineering, where these functional ontologies are often used, but they are handcrafted. And this is useful in two main ways. The first is abstraction. It can allow problem solvers to break out of these fixations to one narrow field and connect the dots so that we can better innovate. And secondly, for reasoning, understanding the interrelatedness of purposes and mechanisms to ask and hopefully answer complex questions on top of this graph. So here actually the subgraph, a kind of small snapshot of what we learned. For example, we have this high-level purpose here of generating power and energy efficiency. And we also have then a sub-purpose of charging batteries and devices. And we have a sub-mechanism of solar power and mechanical stored energy, sustainable sources, and then another sub-mechanism of solar panels and chargers and storage batteries and so on. Now, we need to learn this ontology, and to learn any ontology, we first need a discrete representation of concepts. So we first cluster our purpose and mechanism spans of the text, for example, getting that solar power cluster. And the second thing we need is hierarchical relations, and this we simply do with rule mining in this case. We observe the co-occurrences in our data, and we can, for example, infer that when you see a mention of protecting your head, it entails safety, but not necessarily the other way around by standard rule mining. And to compare against the baseline, we use a baseline that makes use of part of speech tags, for example, based on the fact that verbs tend to correspond more to purposes and noun phrases more to mechanisms. And we first observe a large improvement over the baseline, but importantly, we also see that our performance is now approaching something that we would consider good in more absolute terms. I'm not sure if you can see the figures here, but this, for example, is able to cross the 80% mark. And we observe also substantial judge agreement with respect to the relations we're able to learn with this approach. Second application is building an expressive search engine to boost innovation. So say, for example, you are a light bulb manufacturer and you want to expand to new markets. So you know all the obvious stuff, you know about lights for the office and flashlights. You want to find new areas in which light is not the main purpose. So we, for example, are able to do this with an expressive language that you wouldn't really get in standard search by allowing you to search for products that have similar mechanisms, but purposes that do not include light. So for example, we get a product for warning signs on foods using light. Or we also were able to retrieve a UV light sanitizer that kills bacteria. You can also directly think about using this in scientific papers, of course. Now, technically, we work on top of a set of purposes and mechanisms and query terms. We define distance metrics over them and solve optimization approaches corresponding to retrieval. And to evaluate, we take search scenarios that are common in ideation. For example, using light for the purpose of cleaning. We have these kind of templates. And then we compare against standard search and also our own previous work that uses those soft aggregate purpose and mechanism vectors to see how much the finer grained resolution was able to help us. And we observe that we have better search expressivity using our approach versus our baseline and the standard search embedding-based retrieval. Okay, so I'm going to summarize the first part of this talk. We spoke about models taking in the raw text. We then added some more structure for purposes and mechanisms. We then moved on to finer grained representations. And in terms of applications, we spoke about ideation, boosting creativity with analogies, boosting science, building a functional ontology from purposes and mechanisms, and expressive search for inspiration queries. And this, of course, is done with the help of my colleagues, both at the Hebrew University and at Carnegie Mellon University. Okay, so let's take a deep breath. I'm moving on to the second part of this talk, where we discussed first boosting innovation, and now we want to identify innovation. And we'll do this with a weak supervision framework we developed. Okay, so let me focus on the high-level motivation here. We're focusing on patents again. And this is something we're working on right now. So the problem with identifying true innovation in patents is that labels are extremely hard to obtain. So patent novelty is a hard concept to begin with. It's quite ill-defined. And you could take a patent and all its prior art and show it to an expert, and you still would have a very hard time getting a rating for how novel a patent is. Now, you could just ask, why not use citations? Well, at least in this room, I'm sure that a lot of us know that citations are a pretty weak proxy for innovation. And another problem, this happens in patents drastically, but also in science. And citations often, in addition to other biases and problems, tend to be delayed. And sometimes the community doesn't even realize at all the innovative potential in an idea. But the good thing about weak proxies is that they are easy for us to obtain. And in this case, we'll focus on aggregate patent portfolio information. So we can know from prior economic research, for example, that the average proportion of novel patents is very, very small. We also know intuitively that some organizations are more innovative than others. For example, I'm sure most of you know this academic institute here on the right, and you can just know that it has a higher average proportion of novel patents in their portfolio, in all likelihood, than some other institution. And you want to go from this aggregate information to predicting at the individual patent level. So telling us, for example, that a patent about autonomous cars is more innovative than reinventing the wheel. Now, obtaining labels is generally a difficult task. We often have no access to ground truth information at all. So you could take some user behavior on an app, for example, and ask them, you give this data to an expert and ask the expert, can you ascertain who the user voted for or what are the user's health conditions? Well, sometimes the information just isn't there. Now, we have privacy issues that often come up. Showing crowds or experts data is often not possible. In general, crowdsourcing is not a cure-all. Workers are not domain experts, and I'm sure we all know that it can be a really difficult, noisy, and especially a costly process. On the other hand, rough aggregate information is often much easier for us to obtain. So we're developing a framework where you can use this rough aggregate information, and we call it ballpark learning. The name ballpark comes from an educated guess or estimation that falls within acceptable bounds. It comes from an analogy to baseball. I hear some of you were at a baseball match yesterday, and we just love analogies, so we had to include this. And in its general form, ballpark learning is based on the following. We have our training instances, X, with unknown labels, Y. And our instances are divided into K bags, for example, patent portfolios. And in our framework, we are now enabling constraints on unknown label averages. For example, the average proportion of novelty in some portfolio. We also enable difference constraints about differences between bags, which can be encoded in various ways. And our goal is to predict instance level labels from these rough constraints on label averages. Now let's first look at the classification formulation we created. So we have a discrete binary label space. This can also be extended to the multi-class setting. And we solve the following biconvex optimization problem. Now let's understand some details. We have our objective function here. This includes a hinge loss term, but also slack variables to allow for the case where you may have some labeled data. And we also have our proportion constraints. Now, intuitively, this objective helps us find an assignment to the latent vector of labels Y that accurately matches model predictions. And the linear constraints help ensure a correct assignment to the vector Y so that it falls within our feasible set dictated by the ballpark constraints. And we solve this biconvex problem with a coordinate descent alternating optimization approach. Now, we also have a formulation for the continuous label space for regression, now with the advantage of being convex, in fact quadratic with respect to the hidden labels Y, which allows all kinds of fast solutions. I won't go into that. And we also have an alternative formulation where we optimize only for the model weights under feasibility constraints, which we impose on the model predictions themselves. Now we have much less parameters and a faster solution. We also have a probably approximately correct formulation with a sample complexity bound that comes with it. And with more details and discussions, you can check out our wisdom paper. Okay, one final note is about hyperparameter optimization. So in standard hyperparameter optimization, we need labeled examples. How do we do this here? So we develop a scheme we call constraint violation cross-validation grid search, where we run k-fold cross-validation. We split our bags into training and held-out bags. Then we're going to make the assumption that because we sampled uniformly, we're going to assume that the label proportions also remained approximately the same in the training and the test bags. And then we'll measure our constraint violation on these held-out bags. So how far off our model's predictions were from the ballpark constraints. And we'll take a look at the set and we'll pick the hyperparameter with a minimal average violation. So our end game is patents, but first we evaluate across lots of benchmarks. We have labeled examples and lots of things to compare to. For example, this is just a small sample. We predict recidivism, return to prison according to groups of inmates, such as based on their prior record. We predict prices of apartments on Airbnb according to neighborhoods and other simple attributes of apartments. We also do prediction in a socioeconomic setting. And to get a bit more feeling, I'll just dive quickly into this one. So say you want to predict income as being either high or low in the well-known census data set. But now we're going to emulate an example where we don't have any labels at all. But we do have bags based on education and gender. And we can build our ballpark constraints, for example, coming from surveys or previous census data or sampling or even intuition. For example, we may know that PhDs have higher income than in the overall population. I'm told, that's what my advisor tells me. I really hope that's true. And we have all kinds of other constraints, and we use them to build our bags. And importantly, bags do not necessarily have to be used as features. So at test time, the model can predict the label without knowing the education level for a new incoming instance. So we first see in our evaluation that we need quite a lot of labeled examples in standard learning, for example, in SVM, to match what we can get with no labeled data at all. And the second thing we compare to is a kind of niche field in machine learning called learning from label proportions, which some of you may know, where a much stronger assumption is made about knowing exact label proportions. And we show that we can rival all kinds of baselines in this approach, published first in JMLR, where we use much weaker information. Now, where do we get our constraints? We emulated the example. We have expert knowledge constraints. You could also think about crowdsourcing. We can pool noisy crowd guesses on intuitive groups. For example, we ask the crowd to predict return to prison, the likelihood based on simple groups of prisoners. Or we ask the crowd to predict ranges of prices of apartments on Airbnb according to simple groups of apartments. And the bottom line is that our results rival supervised models that use many true labels. And also, when we run experiments asking the crowd to guess on individual instances, showing them more information than what we are exposed to, for example, apartment attributes on Airbnb, we get really poor results when feeding that into our model. We're able to pool these guesses in a more smart way. And we also do this with a total cost that is more than 3 times less than the standard labeling approach of collecting individual guesses, because our questions are able to cover many instances at once with kind of a weak signal. So a quick question, do I have until 10:45 or the whole hour? How does it work?
The whole hour.
Okay, because I'm trying to go a bit faster, so I'll slightly slow it down. So when would you use ballpark learning? Well, when you have no labels, first of all, only rough information on groups, and also when crowdsourcing for individual labels is hard. So we need much less domain expertise because we're relying on this human intuition on groups and comparisons, which is studied in psychology. We ask fewer questions, thereby cutting costs. We have virtually no privacy concerns because we never really show any individual instances to the crowd. And our approach can also help with other real-world characteristics and challenges that come up in crowdsourcing on real data that we discuss in our wisdom paper. Now, importantly, our approach can help complement standard crowdsourcing when it faces the kind of difficulties that come up in these kind of scenarios. Okay, so to wrap up the part about ballpark learning, we're now returning to our main end game of evaluating on patterns, identifying those novel patterns. And where do our constraints come from? Well, they can come from economic research, rich economic literature telling us something about the distribution of novelty across different categories of patents. We have company rankings and institution rankings according to how innovative they are. And we can use this to build our constraints and build our bags. Another thing ballpark learning needs is features. So we first connect back to our work on analogies, and we look for patterns that combine distant mechanisms or use mechanisms for far purposes. These are indicators of novelty. We also enrich our feature set with pattern citation network features and textual representations. And we find one more challenge. Because we have a small number of truly novel patterns, we find that we need to gain a finer control on the distribution. So instead of looking at the averages, we're going to constrain the tails, and we look at the sum of the top K patents. For example, when we want to compare two institutions, we won't compare their overall average, but we'll compare the top of their distribution. Now, this is a convex function, but using them this way leads to a violation of convex programming. But luckily, we have dedicated optimization approaches for this scenario. Now, as I said, this is work in progress. But our initial results are showing that we get higher indicators of novelty for the patterns we retrieve with our approach, better than anomaly detection in some cases. And now we're making this more concrete by going to pattern examiners to evaluate and collect more labeled data, and this is happening now. Okay, so in the few minutes I have left, I'll quickly discuss some future work and my own broader interests in taking this work forward. First, in terms of analogies, we want to develop richer NLP models and representations to capture analogies. For example, learning to extract graphs from patents and products, capturing how purposes and mechanisms interrelate, or incorporating in external common sense knowledge graphs so that we can control abstraction in a better way and find better analogies. We've also started working on a live search engine for researchers, engineers, and the general public to find ideas this way. And in our ballpark approach, we showed our non-convex extension for patents, which we're working on. And we've also started working on learning deep neural network representations from rough aggregate constraints on groups rather than having to collect many, many individual instances as we usually do. Now, in terms of my interest in taking this forward, I'm interested in developing new models for complex texts and behavioral data that could come up in scientific knowledge discovery, in health, in social science, and in psychology. Now, that's quite a lot, so I'll just give a few examples. In terms of modeling complex texts, we spoke about scientific papers, we spoke about patents. Obviously, there are many more examples. For example, conversations evolving over time, medical transcripts and documents. And hierarchical graph neural networks, which are a promising direction in NLP, could be useful by propagating fine-grained information across long spans of the text, but also perhaps allowing us different resolutions of the document that we can capture this way. Now, one example I'm interested in is a multimodal fusion of search behavior with scientific paper content. So, you know, for example, when you have a new idea and you go to Semantic Scholar or one of those other competitors, and you want to find if your idea is out there. So we can take all this search data coming from many researchers and kind of treat it like researcher gradient descent. So we're observing how people search for ideas over time. Can we learn to predict this process, to model it, to discover it, to point us in interesting directions in the space of ideas, and also help boost the discovery process of individual users as we go. And graph neural networks could be useful by, in a structured way, fusing the search behavior with fine-grained information in the documents. Another interesting component is to incorporate external world knowledge into our NLP models. Of course, a big problem in NLP, and graphs could be a useful approach to do this in a structured, fine-grained manner. Now, we spoke about boosting innovation. Another way to do so would be by modeling how innovation actually takes place. So can we predict the trajectories of science? Observe this dynamic, heterogeneous graph of scientific knowledge For example, the one that you have here in Semantic Scholar, and ask questions such as, can we predict the path of experts? So what will your next papers be about? Can we predict this? This will have applications both for modeling how science evolves, but also for helping improve the discovery process. Can we identify structural holes in this rich graph of knowledge? So places where it's interesting to look at for new ideas, perhaps connecting the dots between fields, and not any connections. You could come up with any kind of crazy idea like bicycles for elephants. Well, someone's already thought of that one. And secondly, right, who cares? We need the high value research potential. And how do we define that? How do we model these places in the space of ideas? And finally, can we learn generative models of ideas? Can we learn models that are able to capture how these ideas evolve and form over time? For example, learning how to compose ideas or amplifying certain aspects of ideas so that we can sample from these models in a controlled way, pointing us to interesting directions in space. Last slide about this. We spoke about identifying novelty in science and in technology, but we can also think in a bit more abstract terms about general novel social phenomena and health-related phenomena, new concepts, new misconceptions. For example, the anti-vaccination movement. Can we model it from online discussions, from online texts, understand it, discover it, predict its evolution? Can we predict collective behavior and decision-making from group conversations? In particular, identifying group dynamics and latent individual roles that are studied in psychology by looking at how people speak to each other? And more generally, discovering new health and psychological behaviors, symptoms, and causes from this rich kind of data, online discussions, and texts. One final note, we spoke about health and social knowledge discovery. I'll also quickly note that I've been leading an applied research team in industry, working on NLP, computer vision, and graph machine learning for areas such as healthcare, knowledge discovery from the social media and web. For example, we recently published an adaptive fusion of pre-trained vision and NLP models for transfer learning across all kinds of tasks with a mixture of experts framework, but I will not go into that right now. So, to conclude, we spoke about boosting innovation with analogies, extracting purposes and mechanisms from real-world noisy texts, products, patents, scientific papers. We use that to enhance creativity, build expressive search, build common-sense functional ontologies. And we also developed a new weak supervision framework, working with rough group information on label averages. We evaluated across many regression and classification tasks. And now we're working on a non-convex extension for patents to identify novel ideas. And in terms of broader interests, we discussed modeling complex text in general and behavioral data for knowledge discovery in science, in health, and novel social phenomena. Thank you.